The most powerful telescopes on Earth have turned their gaze away. The sun, they say, is too bright, too dangerous to observe. Convenient words for silence. But amateur astronomer Tiago, alias Dobsonian Power, didn't listen. From his backyard, he aimed his lens straight into the glare, and what he captured changes everything. The amateur images he and some of his viewers captured reveal something NASA didn't, or rather wouldn't say. A dark, geometric shape. A triangular object where physics says none should exist. Tonight, we step into his mystery, and into the possibility that 3I-ATLAS isn't just another comet, and the triangular object is one of its smaller probes refueling in plain sight at our sun. So close your eyes, breathe slowly, and stay until the end. Because if what we've uncovered is true, NASA's silence isn't caution, it's confirmation of what we have all been thinking. If this story has you on edge like it has me, don't just sit in the shadows, hit like, subscribe, and stay locked in, so you don't miss a single update as this unfolds in real time. Tell me in the comments where you're tuning in from, what time it is there, and whether you think we're being told the truth about what's really out there. And if you believe more people deserve to know, share this video on X, Reddit, Facebook, anywhere the conversation can't be silenced. You're the reason we can keep chasing stories like this, so thank you for having our back. Part 1. Bombshell. You are looking at something NASA does not want you to see. Right now, somewhere in the glare of our sun, there is an object. Scientists call it 3I-ATLAS, the third confirmed interstellar visitor to our solar system. It came from beyond, travelling faster than anything bound by our star's gravity should travel. And according to one amateur astronomer in Texas, it is not alone. His name is Chris Green, and the photograph he captured will change everything you thought you knew about what is passing through our cosmic neighbourhood. This is not a story about distant possibilities or mathematical probabilities. This is happening now. The object in question made its closest approach to Earth in recent weeks, and within days it will vanish behind the sun's overwhelming brightness, disappearing into what astronomers call solar conjunction. For weeks, maybe months, we will be blind to it, and when it emerges on the other side, if it emerges, we may never get another chance to see what it really is. The man leading this investigation is not a professional astronomer. His name is Tiago, and he runs a YouTube channel called Dobsonian Power. He owns a backyard telescope, streams his observations live, and has spent the last several weeks trying to do what he claims NASA will not do, which is to actually look at this thing with enough scrutiny to determine whether it is natural or something else entirely. His accusation is simple and devastating. He believes the agency is hiding behind bureaucratic excuses, specifically a supposed government shutdown that conveniently prevented the release of high-resolution imagery from the Mars orbiter team right when 3I-ATLAS was at its most observable. He says they are lying to us, and he has been trying to prove it. But Tiago's own attempt did not go as planned. Using a specialised solar telescope designed to observe prominences and flares at the edge of the sun, he pointed his equipment toward the coordinates where 3I-ATLAS should have been visible. What he captured was underwhelming, a faint blob, a smudge, something that moved between observation sessions, convincing him it was not dust on his lens, but also something so indistinct that he could not, in his own words, claim anything definitive. He was honest about it. He told his viewers he had failed. The object was there, or something was there, but his equipment could not resolve it. The glare was too strong. The filters were not right. The mystery remained unsolved, and then Chris Green sent him a message. Chris is a viewer, a member of the community, someone with his own telescope and a different approach. Instead of using a prominent scope designed for the solar atmosphere, Chris used a standard telescope equipped with a Herschel wedge, a specialised filter that allows you to safely photograph the sun's surface, the photosphere, where sunspots form. This type of imaging is common among solar observers. It provides sharp, high-contrast views of surface details. Chris pointed his setup at the same region Tiago had been watching, the area near the sun where 3I-ATLAS was supposed to be transiting, and what he captured was not a faint blob. It was not ambiguous. It was a shape. The image shows a dark, geometric object, perfectly triangular, sitting just off the edge of a sunspot. The angles are clean. The edges are sharp. It does not look like a sunspot. It does not look like a prominence or a filament or any other known solar feature. It looks To put it bluntly, like a pyramid, or a craft, or something engineered. Next to it, in another frame, there is a circular dark object, and in yet another, a wave-like anomaly that defies easy classification. Chris sent these images to Tiago during a live stream, and the reaction was immediate. Tiago stared at the screen, processing what he was seeing, and then said the words that would define the rest of this investigation. "Chris, you won." That moment represents a shift, not just in methodology, but in belief. Tiago, who had been cautious, who had refused to make definitive claims about his own observations, was now willing to change his entire approach based on a viewer's photograph. He announced he would purchase a Herschel wedge. He would replicate Chris's setup. He would go back and try again. The implication was clear. If Chris could capture this, so could he. And if the triangle is real, if it appears again in his images, then the narrative moves from fringe speculation to something far more serious. Because objects do not just appear near the sun in perfectly geometric shapes, not naturally. So what exactly are we dealing with here? Is 3I-ATLAS a comet, as mainstream astronomers insist, or is it something else? And if Chris's triangle is real, what is it doing so close to the sun's surface? The hypothesis circulating in Tiago's community is both simple and staggering. They believe 3I-ATLAS is a mothership, an interstellar vessel, and the triangular object Chris photographed is not part of the comet itself. It is a smaller probe sent down to the sun to harvest energy, refueling, recharging, preparing for the next leg of its journey. You have 5 days left before solar conjunction, 72 hours before the glare becomes too intense for ground-based observation. After that, the object will be invisible to us, hidden behind a wall of light that no filter can penetrate, and when it comes back, if it comes back, we will finally know whether this was a moment of discovery or a moment of delusion. But right now, in this narrow window, the stakes could not be higher. Because if Tiago succeeds in replicating Chris's image, if the triangle appears again, captured by different equipment, from a different location, at a different time, then we are no longer talking about a single photograph. We're talking about evidence. Part 2, Latest Science versus Fringe Narrative. Before we go any further into the conspiracy, into the accusations and the triangle and the refueling theory, we need to establish what is actually known about 3I-ATLAS. Not what people believe, not what they hope, what the science says. Because if we're going to evaluate whether this object is natural or engineered, we need a baseline. We need to know what a normal interstellar comet looks like, and then we need to see where 3I-ATLAS deviates. The object was discovered in early 2025 by the ATLAS survey system, an automated network of telescopes designed to scan the sky for near-Earth objects and anything else moving unusually fast. Its official designation is 3I-ATLAS, the 3 indicating it is the third confirmed interstellar object ever detected. The first was Oumuamua, discovered in 2017, which caused a firestorm of debate due to its bizarre elongated shape and unexplained acceleration. The second was 2I/Borisov, discovered in 2019, which behaved much more like a typical comet and was far less controversial. 3I-ATLAS falls somewhere in between. Its orbit is hyperbolic, meaning it is not bound to the sun. It came from interstellar space, and it will return to interstellar space. The trajectory suggests it originated from somewhere in the direction of the constellation Lynx, though pinpointing an exact origin is difficult over interstellar distances. Its speed, relative to the sun, is around 30 kilometers per second, which is typical for objects not gravitationally bound to our solar system. It is fast, but not impossibly fast. Its closest approach to the sun, called perihelion, occurred in late September 2025, bringing it within approximately 0.1 astronomical units of the sun's surface. That is close. Very close. Closer than Mercury orbits. At that distance, the solar radiation is intense enough to vaporize most ices and subject any solid nucleus to extreme thermal stress. Astronomers estimated the size of the nucleus, the solid core of the comet, to be somewhere between 1 and 3 kilometers across, though this is difficult to measure directly because it is surrounded by a bright coma of gas and dust. The tail, a long streamer of debris blown back by solar wind, has been visible in long exposure images taken by professional observatories. Some observers reported unusual tail morphology, including jets that appeared to shoot directly toward the sun rather than away from it, which is atypical. Brightness fluctuations were also noted. with periods of sudden brightening that did not align perfectly with standard outgassing models. These anomalies are not definitive proof of anything unusual, but they are enough to make professional astronomers take a closer look, and that is where the mainstream story ends. 3I-ATLAS is a comet. It is unusual in some respects, but nothing that cannot be explained by variations in ice composition, rotational dynamics, or surface activity. Science moves slowly, cautiously, waiting for peer-reviewed papers and repeated observations before making bold claims. But online, in the communities watching this object, patience has run out. Because while scientists are analysing spectral data and calculating mass loss rates, amateur observers like Tiago are making a very different argument. They believe NASA and other space agencies are deliberately withholding high-resolution imagery. Tiago's primary accusation centres on a claim that the HiRISE camera team, which operates the high-resolution imaging instrument on the Mars Reconnaissance Orbiter, used a government shutdown as an excuse to delay or suppress images of 3I-ATLAS. The HiRISE team publicly stated during a specific window in late 2024 and early 2025 that they were unable to release new processed images due to federal government operational disruptions. Tiago argues this is too convenient. He points out that the shutdown timing overlapped almost perfectly with the period when 3I-ATLAS would have been most visible to Earth-based and space-based observatories. He suggests that insiders within NASA, people he calls infiltrators, wanted to release the truth but were overruled by higher-level administrators who fear public panic. To evaluate this claim, you would need to cross-reference the exact dates of the government disruptions with the observational windows for 3I-ATLAS. Did the shutdown actually prevent imagery release? Or were images released on schedule but not widely publicised? Was the delay bureaucratic, or was it intentional suppression? These are questions that require access to internal communications, schedules, and data release protocols that the public does not have. What we do know is that space agencies frequently delay data releases for a variety of mundane reasons, including calibration checks, peer review coordination, and instrument downtime. But we also know that controversial discoveries have historically been subject to internal debate before being made public. The question is whether this case fits that pattern. The other complication is solar conjunction. As 3I-ATLAS passed close to the Sun, it entered a phase where observation from Earth became nearly impossible due to the Sun's glare. This is not a conspiracy. This is physics. When an object passes within a few degrees of the Sun as seen from Earth, the overwhelming brightness makes it invisible to most telescopes. Even space-based observatories like SOHO, which are specifically designed to block the Sun's disk, have limited sensitivity near the solar limb. For weeks, possibly months, depending on the object's speed and trajectory, 3I-ATLAS is effectively hidden. This is the solar conjunction blackout, and it is real. But Tiago and his community argue that this blackout is being exploited. They believe NASA is using the physical constraint as cover, extending the silence longer than necessary to avoid public scrutiny. So you have two narratives running in parallel. One says that 3I-ATLAS is an interstellar comet, behaving mostly as expected, with some minor anomalies that warrant further study. The other says it is an engineered object, possibly a vessel, possibly a probe, and that its true nature is being hidden by institutions that do not trust the public to handle the implications. The gap between these narratives is enormous, and the evidence at this stage is ambiguous enough that neither side can fully claim victory, but the tension is building. Because Chris Green's triangle photograph pushes the fringe narrative into new territory. It is no longer just about withheld data or suspicious timing. It is about a specific, visible, geometric object that should not exist if the mainstream explanation is correct. Part 3. Tiago's attempt versus Chris Green's evidence. Tiago's equipment is impressive for an amateur setup. He uses a dedicated solar telescope, the kind designed to image the Sun's chromosphere, the layer of atmosphere just above the visible surface. This type of scope is optimized for viewing prominences, which are loops and arcs of superheated plasma that rise from the Sun's limb. Prominences are spectacular. They look like flames frozen in space, glowing in hydrogen alpha light. But this type of telescope is not designed for high-resolution imaging of the photosphere, the Sun's visible surface where sunspots form. The filters are different. The optics are tuned for a specific wavelength. And while you can use a prominent scope to look near the sun's edge, you sacrifice sharpness and contrast when trying to resolve small details against the bright disk. Tiago knew this going in. He was not expecting perfect clarity, but he was hoping for something. He used tracking software to input the coordinates of 3I-ATLAS based on publicly available ephemeris data from NASA's Jet Propulsion Laboratory. The software calculated where the object should appear in his field of view, just off the edge of the solar disk. He pointed his scope, adjusted his exposure settings, and began capturing frames. What he saw was frustrating. There was something there, a faint, fuzzy anomaly. It was not a sharp object, it was not clearly defined, but it moved. Between observation sessions, the position shifted in a way that dust or sensor noise would not. That movement convinced him it was real, that he was seeing something external, something in space near the sun, but he could not identify it. He could not zoom in enough or filter out enough glare to make a definitive claim. On camera, during a live stream, he admitted defeat. He told his audience he had captured a weird glitch, but it was too indistinct to call proof. He estimated he was 99% sure the earlier detection was real based on positional change, but that last 1% of doubt was enough to keep him from declaring victory. He needed better equipment. He needed a different approach. And that is when Chris Green entered the picture. Chris lives in Texas. He is not a professional astronomer. He is a hobbyist, someone who enjoys solar observation as a side interest. His setup includes a standard refracting telescope, nothing exotic, paired with a Herschel wedge. The wedge is a key piece of technology. It is a prism that reflects most of the sun's light out of the optical path, allowing only a small, safe percentage through to the eyepiece or camera. This drastically reduces brightness and heat, making it possible to photograph the photosphere in white light. The resulting images show sunspots, granulation, and surface details with high contrast. It is a common tool among amateur solar observers, and it works well. Chris used this setup to image the same region Tiago had been watching. He captured multiple frames over the course of an observation session, and when he reviewed the images, he noticed something unusual. There, just off the edge of a prominent sunspot group, was a dark triangular shape. It was not a smudge, it was not a blur, it was sharp-edged, symmetric, and distinctly geometric. The triangle appeared to have 3 clean sides, meeting at precise angles. It did not look like any known solar feature. Sunspots are irregular, filaments are wispy, prominences are looping and chaotic. This was none of those things. It looked artificial. Chris took additional frames showing other anomalies. One image captured a perfectly circular dark object in a different part of the solar disk. Another showed a wave-like structure that seemed to ripple across the surface. He compiled these images and sent them to Tiago during a live stream. Tiago opened the files on screen and the chat exploded. Comments flooded in. People were stunned. Tiago himself paused, staring at the triangle, and then said, "Chris, you won." The tone was not sarcastic. It was not dismissive. It was genuine. He was conceding that Chris had succeeded where he had failed. Chris had captured something definitive. The implications were immediate. If the triangle is real, if it is not an artifact or an optical illusion, then it represents physical evidence of a structured object near the sun during the same window when 3I-ATLAS was transiting. The community quickly adopted the interpretation that the triangle is a probe, a smaller craft deployed by the larger mothership to harvest solar energy. This fits the refueling hypothesis. The sun is an enormous power source. A sufficiently advanced civilization might design interstellar vessels to make close passes, siphon energy through collectors or magnetic scoops, and continue onward. The triangle in this narrative is the collector. It is stationed near the photosphere, absorbing gigawatts of radiation, storing it, and transmitting it back to the mothership. Tiago announced that he would adopt Chris's methodology. He would purchase a Herschel wedge. He would switch from prominence imaging to photosphere imaging. He would attempt to replicate the results. This decision is significant because it represents a shift from skepticism to active investigation. He is no longer just questioning NASA's narrative. He is testing the fringe hypothesis directly. If he succeeds, if his new setup captures the triangle again, then the single image from Chris becomes part of a pattern. It becomes reproducible, and reproducibility is the foundation of scientific credibility. But if he fails, if the triangle never appears again, then Chris's image will remain an isolated anomaly, subject to alternative explanations like optical artifacts, sensor glitches, or misidentified solar features. The stakes are now personal. Tiago's reputation depends on this. His audience is watching, the community is invested, and the clock is ticking. Solar conjunction is approaching, the window is closing. Whatever happens next will determine whether this story becomes a footnote in amateur astronomy or the beginning of something far larger. Part 4, Turning Point, Tiago Concedes. The moment when Tiago said "Chris, you won" was more than just an acknowledgement. It was a pivot, a turning point. For weeks, Tiago had been the skeptic, the investigator, the person demanding better evidence before making bold claims. He had criticised others in the community for jumping to conclusions. He had been cautious with his own observations, refusing to declare victory even when he thought he saw something. But Chris's image changed the calculation. It was too clear, too geometric, too compelling to dismiss. And Tiago, to his credit, did not double down on his original position. He adapted. This kind of shift is rare. Most people, when confronted with evidence that contradicts their expectations, dig in. They find reasons to dismiss the new data. They protect their prior beliefs. But Tiago did the opposite. He accepted that his equipment was inadequate. He acknowledged that Chris had succeeded where he had failed, and he committed to changing his methodology. This is not the behaviour of someone running a grift. This is someone genuinely trying to figure out what is happening, but there is a risk. By conceding to Chris, by elevating a viewer-submitted image above his own observations, Tiago is staking his credibility on someone else's work. If Chris's image turns out to be an artifact, if the triangle is explained as a sensor glitch or an optical effect, then Tiago's decision to adopt the same method will look naive. He will have abandoned his original cautious approach for something that turned out to be false. On the other hand, if the triangle is real, if it appears again in Tiago's new images, then his willingness to adapt will be seen as intellectual honesty. He followed the evidence. He changed course when the data demanded it. That is how science is supposed to work. The community response was immediate and intense. Chat logs from the live stream show a mix of excitement and vindication. Some viewers had been pushing Tiago to take the fringe theories more seriously. They felt validated. Others expressed concern, worried that he was moving too fast, that he was letting enthusiasm override skepticism. A few commenters pointed out that a single image, no matter how compelling, is not proof. They argued that Tiago should wait for replication before committing to the alien probe hypothesis, but the momentum was undeniable. The triangle had captured the imagination of the community, and there was no going back. What makes this moment narratively powerful is the contrast. Earlier in the stream, Tiago had been almost apologetic about his failed observations. He had shown his indistinct blob, explained why it was unsatisfying, and prepared his audience for disappointment. Then Chris's image appeared, and the entire tone shifted. Suddenly there was something concrete to discuss. The conversation moved from maybe something is there to what is that thing. The shift in language reflects a shift in belief. Tiago was no longer investigating a possibility. He was investigating an object. This raises a psychological question. How much of this shift is driven by the evidence, and how much is driven by the desire for the evidence to be true? Tiago and his community want 3I-ATLAS to be something extraordinary. They want NASA to be wrong. They want vindication for years of suspicion and skepticism toward official narratives. Chris's image offers that. It provides a tangible focal point for those desires. The danger is that confirmation bias sets in. Once you believe the triangle is real, every subsequent observation gets filtered through that belief. You start seeing triangles everywhere. You interpret ambiguous data as supporting evidence. You dismiss alternative explanations as too convenient or too mundane. But the counterpoint is this. What if the triangle actually is real? What if the reason it looks artificial is because it is artificial? At some point, skepticism has to give way to investigation. You cannot dismiss every anomaly as an artifact or a misunderstanding. Sometimes the weird thing is weird because it is genuinely weird. And if Chris's image is one of those cases, then Tiago's decision to pursue it aggressively is not bias. It is good instinct. The next live stream will be critical. Tiago has ordered the Herschel wedge. It should arrive within days. He has announced he will conduct another observation session as soon as the equipment is set up and tested. The plan is to point at the same coordinates, use the same exposure settings Chris used, and see if the triangle appears. If it does, the story escalates. If it does not, the community will fracture. Some will argue the triangle was a one-time event, that the probe moved or departed. Others will conclude it was never real to begin with. Either way, the window is closing. Solar conjunction is imminent. The sun's glare will soon swallow 3I-ATLAS entirely. When it emerges, weeks or months later, the object may have changed. It may have moved off course. It may have done whatever it came here to do. Or it may have simply continued on its hyperbolic trajectory, indifferent to the drama unfolding on Earth. Part 5. Cover-up, narrative and motivations. Tiago's worldview does not begin with 3I-ATLAS. It begins with a belief that humanity is being systematically deceived by institutions that claim to act in our interest. He talks about the elite, about power structures, about a corrupted world where truth is controlled by a small number of gatekeepers. In his view, NASA is not a scientific organisation. It is a political organisation. Its primary function is not discovery. It is control. Control of information. Control of narrative. Control of what the public is allowed to believe about the universe. This perspective is not unique to Tiago. It is shared by a significant portion of the alternative astronomy community, the people who follow fringe channels, who distrust official statements, who believe that the most important discoveries are being hidden. The logic goes like this. If an alien spacecraft were detected entering our solar system, the public would panic. Governments would lose control, economic systems might collapse, religious institutions would face existential crises. Therefore, it is in the interest of those in power to suppress the evidence, to frame interstellar objects as natural comets, to delay image releases, to issue vague statements that satisfy curiosity without revealing the truth. The government shutdown excuse in this framework is not bureaucratic incompetence, it is deliberate tactic. Tiago also talks about infiltrators. He believes there are good people inside NASA, scientists and engineers who know the truth and want to share it, but are prevented from doing so by institutional pressure. These insiders, according to Tiago, leak information when they can, feed clues to amateur observers, and wait for the right moment to blow the whistle. He sees himself and others in the community as part of a decentralized resistance, using independent equipment to verify what the insiders cannot say publicly. This narrative is compelling because it reframes failure as virtue. If NASA refuses to release images, it is because they are hiding something. If amateurs capture ambiguous data, it is because they are onto something the establishment does not want revealed. The shutdown claim is worth examining in detail. Tiago references a specific statement from the HiRISE team, the group responsible for the high-resolution camera on the Mars Reconnaissance Orbiter. During a window in late 2024, the team announced that image processing and public releases were delayed due to federal government operational disruptions. This was during a partial government shutdown that affected several agencies, including NASA. The timing overlaps with the period when 3I-ATLAS was approaching the inner solar system and would have been observable by space-based instruments. Tiago argues this is too coincidental. He believes the shutdown was either engineered to provide cover for withholding images, or that it was exploited by decision-makers who wanted an excuse to delay controversial data. To evaluate this, you would need to know whether the HiRISE team actually attempted to image 3I-ATLAS during that period. Mars orbiters are not typically used to observe comets or interstellar objects. Their instruments are pointed at Mars, not deep space. It is possible the team was simply referring to routine Mars imaging delays, unrelated to 3I-ATLAS. But the ambiguity allows the conspiracy narrative to thrive. If NASA or the HiRISE team had released a clear statement saying, "We did not attempt to observe 3I-ATLAS because our instruments are not designed for that purpose," it would have closed the loop. Instead, the silence creates space for speculation. The motive question is central. Why would NASA hide evidence of an alien spacecraft? The standard answer from the fringe community is fear. Fear of societal collapse, fear of losing authority, fear of religious and philosophical upheaval. If humanity learns that intelligent life exists elsewhere, and that it is capable of interstellar travel, the psychological impact would be profound. Some argue that this fear is condescending, that humans are more resilient than institutions give them credit for. Others argue that historical precedent, such as the panic surrounding Orson Welles' War of the Worlds, radio broadcast in 1938, suggests that large-scale misinformation or sudden revelation can indeed cause chaos. The debate is unresolvable without access to internal communications from decision-makers at NASA or other space agencies. Tiago also speculates about technocracy, the idea that scientific and technical elites form a de facto ruling class that hoards knowledge to maintain power. In this view, the public is treated as children, incapable of handling complex truths, while experts make decisions on their behalf. This is a common theme in anti-establishment movements, and it resonates with people who feel alienated from institutional science. Whether or not it is true in this specific case is difficult to prove, but the feeling, the sense that something is being kept from us, is real for many people, and that feeling drives the investigation forward even when the evidence is thin. The infiltration theory is harder to assess. Tiago claims there are insiders feeding information to the community. If true, this would explain how amateurs like him and Chris seem to be ahead of official announcements. But it could also be coincidence. The coordinates for 3I-ATLAS are publicly available from JPL. Anyone with a telescope and the right filters can attempt to observe it. The fact that amateurs captured images is not evidence of insider help. It is evidence that amateurs were paying attention. Still, the narrative of secret allies within the system is emotionally satisfying. It suggests the truth cannot be suppressed forever, that leaks will happen, that the cover-up will eventually fail. And that hope keeps the community engaged. Part 6. Instrumental and optical technicalities. Understanding whether Chris's triangle is real requires understanding how the equipment works and what can go wrong. A Herschel wedge is not a simple piece of glass. It is a precisely engineered optical component designed to split incoming sunlight into two paths. Most of the light, around 95%, is reflected out of the telescope at an angle, dissipating safely. The remaining 5% passes through to the eyepiece or camera sensor. This reduction in brightness is necessary because the sun is so intense that even a fraction of a second of unfiltered exposure can damage your retina or burn a camera sensor. The wedge allows safe observation of the photosphere, the sun's visible surface, where sunspots and granulation are visible. The advantage of a Herschel wedge over other solar filters is image quality. Because the light passes through glass rather than being absorbed by a film or coated filter, there is less scatter and less chromatic distortion. The images are sharp. Contrast is high. You can resolve fine details like sunspot penumbra and light bridges. But the system is not perfect. Herschel wedges introduce their own artifacts. Internal reflections can create ghost images, faint duplicates of bright features that appear displaced from their true position. If you're imaging near the solar limb where brightness gradients are steep, these ghosts can be misinterpreted as real objects. Another potential issue is vignetting, a darkening at the edges of the field of view caused by the wedge's geometry. If you're imaging close to the edge of the solar disk, vignetting can create the appearance of dark patches or shadows that do not correspond to actual features on the sun. You would expect these patches to be circular or smoothly graded, but if the vignetting interacts with a bright feature like a sunspot, the resulting shape can be irregular. A triangular dark region could, in principle, be an artifact of how the wedge's internal prism intersects with a localized bright spot. Sensor noise is another consideration. Digital cameras, especially those used for astronomy, have hot pixels, dead pixels, and read noise that can produce false signals. If you're imaging a low-contrast target near the detection limit, like a faint object in the glare near the sun, noise can create the illusion of structure, post-processing especially. Aggressive sharpening or contrast enhancement can amplify these artifacts. A faint noise pattern that looks like nothing in the raw data can become a distinct geometric shape after processing. This is why professional astronomers always share raw data alongside processed images, so that others can verify that the features are real and not introduced during enhancement. To determine whether Chris's triangle is an artifact, you would need several pieces of information that may not be publicly available. First, the raw image files, not screenshots or compressed JPEGs, but the original unprocessed data straight from the camera sensor. Second, multiple frames from the same observation session, showing the triangle in the same position relative to the sunspot. If the triangle appears in only one frame, it is much more likely to be a transient glitch. Third, metadata about exposure settings, camera gain, and any processing steps applied. And fourth, independent replication. If someone else, using different equipment, at a different location, at a different time, captures the same triangular shape in the same region of the Sun, then the artifact explanation becomes much weaker. Tiago's decision to adopt the Herschel wedge setup is essentially a replication attempt. If he captures the triangle again, using his own equipment, from his own location, that would be significant. But it would still not be definitive. Both observers are amateurs. Both are motivated by the desire to find something unusual. Both are part of a community that has already decided to some extent what they expect to see. Ideally, you would want a professional observatory, one with calibrated instruments and established protocols, to point at the same coordinates and confirm or refute the presence of a dark triangular object. That has not happened yet. Professional solar observatories like the Solar Dynamics Observatory in space, or ground-based facilities like the Daniel K. Inouye Solar Telescope, produce continuous high-resolution imagery of the Sun's photosphere. These images are publicly archived. If a triangular object were present near the coordinates Chris observed, it should, in principle, be visible in those archives. But searching for it requires knowing exactly when Chris made his observation, and exactly where on the solar disk he was pointing. If that information is not available, or if the professional archives were not imaging that specific region at that specific time, then the lack of confirmation is not evidence of absence. It is just absence of evidence. The wave-like anomaly Chris captured is similarly ambiguous. Wave patterns can appear on the Sun's surface due to magnetohydrodynamic oscillations, essentially ripples in the plasma caused by subsurface convection or magnetic field disturbances. These are well-studied phenomena, but they are usually visible in specific wavelengths, like Doppler imaging or magnetogram data, not in white light photosphere images. If Chris's wave anomaly appears in white light, that would be unusual. It could be a real discovery of a previously unrecognized surface feature, or it could be an artifact of atmospheric turbulence causing distortion in the telescope's view. The circular dark object is easier to explain. It could be a small sunspot that appears perfectly round due to the angle of observation, or it could be a filter artifact, a ghost image of a brighter feature displaced to a different part of the frame. Without additional context, it is impossible to say, but the fact that Chris captured multiple anomalies in a single session, each with different geometries, is itself interesting. It suggests either that he is an exceptionally lucky observer, catching multiple rare events simultaneously, or that his imaging setup is prone to producing artifacts. The third possibility, that all of these anomalies are real, and that the region near the Sun where 3I-ATLAS is transiting is genuinely full of unusual structures, is the one the community has embraced, but it is also the least parsimonious explanation. Part 7. Trajectory. Oddities and Hypotheses. The orbital mechanics of 3I-ATLAS are on paper unremarkable for an interstellar object. It is travelling on a hyperbolic trajectory, meaning its total energy relative to the Sun is positive. It came from beyond the solar system, swung past the Sun, and will leave the solar system. This is exactly what you would expect from an object not gravitationally bound to the Sun. The eccentricity of its orbit, a measure of how elongated the path is greater than 1, confirming the hyperbolic nature. Its orbital inclination, the angle between its path and the plane of Earth's orbit, is moderately tilted but not extreme. Objects from the Oort cloud or interstellar space can have any inclination, so this by itself is not unusual, but there are details worth scrutinizing. The perihelion distance, the closest approach to the Sun, is about 0.1 astronomical units, which translates to roughly 15 million kilometers. That is very close. For comparison, Mercury, the innermost planet, orbits at an average distance of 0.39 astronomical units. 3I-ATLAS passes well inside Mercury's orbit, subjecting itself to intense solar radiation and gravitational tidal forces. Most comets that pass this close either disintegrate or show signs of severe thermal stress. The fact that 3I-ATLAS survived perihelion intact suggests either a very robust nucleus, perhaps composed of more refractory material than typical ices, or an unusual internal structure. Another interesting detail is the timing of brightening events. Comets typically brighten as they approach the Sun due to increased sublimation of ices. The brightness should correlate smoothly with heliocentric distance, following a well-understood power law. but observers noted that 3I-ATLAS exhibited irregular brightness spikes, periods where it brightened more rapidly than expected, followed by dimming phases. Some of these spikes occurred near perihelion, which is expected, but others occurred at distances where cometary activity should have been less pronounced. This kind of variability can be explained by uneven surface activity, where jets turn on and off as the nucleus rotates and different icy patches face the Sun. But it can also, if you are inclined toward the artificial hypothesis, be interpreted as evidence of active systems cycling on and off, thermal management protocols, or energy collection phases. The most provocative claim regarding the trajectory comes from community analysis of astrometric residuals. These are the differences between where the object should be based on gravitational calculations and where it actually appears in observations. For a purely gravitational orbit, the residuals should be small, within the margin of observational error. But if an object experiences non-gravitational forces such as outgassing thrust or deliberate propulsion, the residuals grow larger and follow a systematic pattern. The classic example is Oumuamua, which showed measurable non-gravitational acceleration that caused months of scientific debate. Some attributed it to comet-like outgassing that was simply too faint to detect visually. Avi Loeb, the Harvard astrophysicist, proposed it might be a light sail pushed by solar radiation pressure. Has 3I-ATLAS shown similar non-gravitational acceleration? The answer is unclear. No peer-reviewed paper has yet published detailed astrometric analysis with error bars. Amateur trackers in the community claim they have noticed small positional offsets, but without access to raw astrometric data from professional observatories, it is impossible to verify. If the object is under intelligent control, if it is capable of making small course corrections, those adjustments would show up in the residuals. They would be subtle, perhaps only a few kilometers over weeks of observation, but they would be systematic. The challenge is distinguishing genuine non-gravitational acceleration from measurement error, or unmodelled forces like solar wind pressure. Let us entertain the hypothesis. If 3I-ATLAS were an engineered probe, what would its trajectory tell us about its mission? The close perihelion suggests energy harvesting is plausible. At that distance, solar irradiance is approximately 70,000 watts per square metre. If the object has a cross-sectional area of, say, 10 square kilometres, it would intercept roughly 700 gigawatts of solar radiation. That is an enormous amount of power, equivalent to hundreds of large nuclear reactors. Even if the collection efficiency were low, say 1%, you would still harvest multiple gigawatts. For an interstellar probe with advanced energy storage, a single close pass might provide enough power to operate for years or even centuries. The trajectory also suggests intentionality in another way. The orbit's inclination and perihelion timing mean that 3I-ATLAS approached from a direction that minimized detection time. It came from the direction of the Sun as seen from Earth, meaning we could not observe it until it was already very close. If you wanted to enter a solar system without being noticed until the last moment, that would be a smart approach. Once detected, the object moved quickly toward perihelion, spent only a brief time at close range, and then began its exit. The entire observable window is measured in weeks, not months. If this were a reconnaissance mission, a quick pass to gather data and resupply, the trajectory would make sense. But the counter-argument is equally strong. Hyperbolic orbits from interstellar space can have any inclination, and any perihelion distance, depending on where the object originated and what random gravitational perturbations it experienced during its journey. The fact that this one happens to pass close to the Sun does not require an intelligent explanation. It is well within the range of natural variation. The lack of confirmed non-gravitational acceleration, assuming that remains true as more data comes in, also weighs against the artificial hypothesis. Real spacecraft make course corrections. They adjust their orbits. If 3I-ATLAS were under active control, we should see evidence of thrust maneuvers. So far we do not. The community has also speculated about what 3I-ATLAS might do after perihelion. If it is an engineered object, does it have a destination? Is it heading toward a specific star system? Or is it wandering, visiting multiple systems over millennia? The outgoing trajectory, once calculated with sufficient precision, will reveal its future path. If it happens to be heading toward a nearby star system, that might add weight to the artificial hypothesis. If it is heading into empty interstellar space with no obvious target, that would be less suggestive. But again, this is reading intention into randomness. Objects can travel through space for billions of years without destinations. The universe is mostly empty. Most trajectories lead nowhere. What would tip the scales? A detectable signal. If 3I-ATLAS or any associated object like Chris's triangle emitted radio waves, infrared pulses, or any kind of coherent electromagnetic radiation that could be distinguished from natural sources, that would be game over. The debate would end. SETI researchers have protocols for exactly this kind of detection. They monitor known interstellar objects for anomalous signals. As far as public records indicate, no such signal has been detected from 3I-ATLAS. But the absence of a detected signal is not proof of absence. Perhaps the signal is too faint. Perhaps it is directional, beamed somewhere other than Earth. Or perhaps there is no signal because there is nothing to signal. Part 8. Community Law and Fringe Theory. Deep Dive. Beyond Tiago and Chris Green, there exists a sprawling online ecosystem of enthusiasts, speculators, and self-taught analysts who have built an entire mythology around 3I-ATLAS. These are people who spend hours poring over publicly available data, plotting brightness curves, analysing spectral lines, and searching for patterns that mainstream astronomers might have missed. Some of these efforts are rigorous and methodical. Others drift into numerology and wishful thinking, but all of them share a common belief that something important is being overlooked, and that if you look hard enough, the truth will reveal itself. One of the more elaborate theories circulating in these communities involves Fibonacci sequences. The claim is that the brightness variations of 3I-ATLAS, when plotted over time, exhibit peaks and troughs that align with Fibonacci ratios. The Fibonacci sequence, where each number is the sum of the two preceding numbers, appears frequently in nature, from spiral galaxies to the arrangement of seeds in a sunflower. The idea that an alien probe might encode signals using Fibonacci is based on the assumption that any sufficiently advanced civilization would recognize these mathematical patterns as universal, a kind of cosmic language. If the brightness peaks occurred at intervals matching Fibonacci numbers in days or hours, that would, in theory, suggest intentional modulation rather than random outgassing. The problem is verification. Fibonacci ratios are common enough that if you look at any noisy dataset with enough flexibility, you can find apparent matches. This is called the Texas sharpshooter fallacy, where you draw the target around the bullet holes after firing. To prove that 3I-ATLAS is encoding Fibonacci signals, you would need to predict the next brightness peak based on the pattern, and then observe it occurring exactly when predicted. If the predictions fail, the hypothesis collapses. As far as I can tell from community discussions, no one has successfully made and confirmed such a prediction. The pattern matching is post hoc, applied after the fact to data that has already been observed. Another thread of speculation involves prime numbers. Some community members claim that certain brightness spikes occur at time intervals corresponding to prime number sequences, another potential universal marker of intelligence. The logic is similar to the Fibonacci argument. Prime numbers are mathematically fundamental. Any civilization capable of interstellar travel would understand primes. Encoding signals using prime intervals would be a way to announce, "We are here, we are intelligent, pay attention." But again, the evidence is anecdotal. No one has published a rigorous statistical analysis showing that the observed brightness pattern deviates significantly from what would be expected from random comet activity. Tiago himself has been critical of Avi Loeb, the Harvard astrophysicist who has become the public face of the alien probe hypothesis for interstellar objects. Tiago accuses Loeb of recycling old data and repackaging it as new discoveries to maintain media attention. There is tension here because Loeb's methodology, using anomalous observations as starting points for exotic hypotheses, mirrors what Tiago and the community are doing. The difference is institutional backing. Loeb has academic credentials, access to peer review, and a platform within mainstream science. Tiago operates outside that system. He resents what he sees as Loeb's ability to make speculative claims without facing the same level of skepticism that fringe theorists endure. Yet both are asking the same fundamental question: could this object be artificial? The internal contradictions within the community are fascinating. On one hand, there is deep distrust of institutions like NASA and mainstream academia. On the other hand, the community relies heavily on data from those same institutions. JPL provides the orbital elements. Space observatories provide the imagery. Without NASA's data, there would be nothing to analyse. This creates a paradox. The institutions are simultaneously accused of hiding the truth and celebrated when they release data that can be reinterpreted to support alternative narratives. It is a relationship of dependency and antagonism. Some community members have built elaborate mathematical models attempting to extract hidden signals from publicly available photometry. These models incorporate Fourier analysis, wavelet transforms, and other signal processing techniques to search for periodicities or patterns in the brightness data. A few claim to have found repeating signals with periods matching known physical constants, like the fine structure constant or the ratio of electron to proton mass. The idea is that an advanced civilization might embed these constants into a signal as proof of its artificial origin. But professional astronomers who have reviewed these claims, when they bother to review them at all, generally find that the patterns are artifacts of the analysis methods, not features of the data itself. The credibility question looms large. How much of this analysis is rigorous, and how much is motivated reasoning? When you desperately want to find a signal, you lower your threshold for what counts as evidence. You become less critical of your own methods. You interpret ambiguous results as confirmatory. This is not unique to fringe communities. It happens in mainstream science too. But the difference is that mainstream science has institutional safeguards, peer review, replication requirements, standards that force researchers to confront their biases. The fringe operates without those constraints, which allows for more creativity and faster iteration, but also more unchecked error. What keeps the community engaged despite the lack of definitive proof is the sense of being part of something larger. These are people who feel alienated from institutional science, who believe they have been lied to, who want to reclaim agency by conducting their own investigations. The social bonds formed in these online spaces are real. The shared sense of mission is real. Whether or not 3I-ATLAS turns out to be an alien probe, the community has created meaning and purpose around the search. That cannot be dismissed as mere delusion. It is a genuine human response to uncertainty and the desire for discovery. Part 9. Comparisons. Historic cases. 3I-ATLAS is not the first interstellar object to provoke speculation about artificial origins. It is part of a lineage, a pattern of discovery and controversy that began with Oumuamua in 2017. Oumuamua was the first confirmed interstellar visitor, a small elongated object that tumbled through the inner solar system at high speed and then vanished back into deep space. Its discovery was accidental, caught by the Pan-STARRS survey in Hawaii just as it was already leaving. By the time astronomers realized what they were looking at, the object was too far away for detailed study. But what little data they collected was strange. Oumuamua exhibited non-gravitational acceleration. It deviated from a purely gravitational trajectory in a way that suggested an additional force acting on it. The leading explanation was outgassing, the same process that propels comets. But Oumuamua did not have a visible tail or coma, the hallmarks of active cometary behaviour. It looked more like an asteroid, yet asteroids do not accelerate. This discrepancy led to months of scientific debate and multiple competing hypotheses. Some proposed that Oumuamua was made of solid nitrogen ice, which would sublimate without producing a visible tail. Others suggested it was a hydrogen iceberg, a theoretical construct made of molecular hydrogen that would be nearly invisible as it outgassed. Avi Loeb proposed the most provocative hypothesis. He suggested that Oumuamua might be an artificial light sail, a thin reflective membrane pushed by solar radiation pressure. Light sails are a real concept, proposed for human interstellar missions. If an advanced civilization built such a device, it might appear similar to Oumuamua, flat and elongated with high surface area to mass ratio. Loeb's hypothesis was not definitive. He framed it as a possibility worth investigating, not a conclusion. But the media ran with it, and Oumuamua became synonymous with the idea of alien probes. The scientific community largely rejected the hypothesis, not because it was impossible, but because natural explanations, while imperfect, remained more plausible. 2I/Borisov arrived 2 years later in 2019. This object was far less controversial. It looked like a comet. It had a bright coma and a long tail. It showed all the expected signs of outgassing. Spectroscopic. Analysis revealed water vapour, carbon monoxide, and organic compounds, the same materials found in comets native to our solar system. 2I/Borisov was interesting because it confirmed that comets exist around other stars and that they can be ejected into interstellar space. But it did not challenge any fundamental assumptions. It was a data point, not a mystery. The lesson from these two objects is that interstellar visitors exist, but they are rare and fleeting. Detecting them requires luck and vigilance. Most pass through the solar system unnoticed. Of the two we have studied in detail, one was ambiguous enough to spark debate, and the other was unremarkable. 3I-ATLAS now represents a potential third act in this saga. It combines elements of both predecessors. Like Oumuamua, it has orbital and brightness anomalies that feed speculation. Like Borisov, it shows signs of cometary activity, the volatiles and tail structure you would expect from a natural object. But unlike either, 3I-ATLAS has an amateur community actively imaging it in real time, and that community claims to have captured direct visual evidence of an artificial structure. If Chris Green's triangle is confirmed, 3I-ATLAS will surpass Oumuamua as the most controversial interstellar object ever detected. Oumuamua's anomalies were indirect, inferred from acceleration data and brightness measurements. The triangle, if real, is direct. It is an image of a geometric object. That is a different category of evidence. It would force mainstream astronomers to either provide a plausible, natural explanation or acknowledge that the artifact hypothesis deserves serious consideration. But if the triangle is debunked, if it turns out to be an optical illusion or sensor glitch, then 3I-ATLAS will join Borisov in the category of interesting but ultimately ordinary interstellar comets. The historical pattern suggests caution. Extraordinary claims about interstellar objects have a poor track record. Oumuamua's alien light sail hypothesis did not gain traction in the peer-reviewed literature. Most astronomers treat it as an interesting thought experiment, not a viable explanation. The danger for the 3I-ATLAS community is that they are setting themselves up for a similar outcome. By investing heavily in the triangular probe hypothesis, they risk being dismissed if the evidence fails to hold up. But the potential reward, if they are right, is vindication on a scale that would redefine humanity's place in the universe. What would it take to cross the boundary from fringe speculation to mainstream acceptance? First, repeatability. Multiple independent observers would need to capture the triangle or similar geometric structures using different equipment at different locations. Second, peer review. A professional astronomer with access to calibrated instruments would need to confirm the observations and publish the results in a reputable journal. Third, exclusion of artifacts. Detailed analysis would need to rule out optical effects, sensor glitches, and post-processing errors as explanations for the triangular shape. Fourth, coherence. The observations would need to fit within a broader framework of data, including spectroscopy, polarimetry, and trajectory analysis, all pointing toward an artificial origin. None of these criteria have been met yet, but the clock is still running. Part 10. Energy harvesting theory around the Sun. The hypothesis that 3I-ATLAS or its associated probes are harvesting solar energy is rooted in basic physics. The Sun is the most abundant energy source in the solar system. At Earth's distance, solar irradiance is about 1300 watts per square metre. At 3I-ATLAS's perihelion distance of 0.1 astronomical units, the irradiance is roughly 100 times stronger, around 130,000 watts per square metre. If you had a collecting surface even a few kilometres across, you could harvest gigawatts of power. For an interstellar probe travelling between star systems, where energy sources are scarce, a close pass by a star to refuel would be a logical strategy. Let us calculate. Assume the triangular object Chris captured has a side length of 100 metres. That is small, roughly the size of a large building. The surface area of an equilateral triangle with that side length is about 4,300 square metres. At perihelion, with irradiance of 130,000 watts per square metre, the triangle would intercept approximately 560 megawatts of solar radiation. If it were a perfectly efficient solar collector, which is impossible but useful for setting an upper bound, it could harvest over half a gigawatt. Even with a realistic efficiency of 10%, that is 56 megawatts. Over the course of a few days near perihelion, the total energy collected could reach several terajoules, equivalent to the energy content of hundreds of tons of chemical fuel. For comparison, the International Space Station's solar arrays generate about 100 kilowatts, enough to power the station systems. Chris's triangle, if it were a functioning solar collector, would generate over 500 times more power. That is enough to run massive onboard systems, charge energy storage banks, or even power a propulsion system for course corrections. The numbers suggest that solar energy harvesting near the Sun is not just plausible, but potentially very effective for an advanced spacecraft. But there are engineering challenges. At that proximity to the Sun, the temperature of any exposed surface would be extreme. Without active cooling or highly reflective materials, most substances would melt or vaporize. The triangle, if real, would need to be constructed from refractory materials capable of withstanding temperatures exceeding 1,000 degrees Celsius. It would also need to manage thermal gradients preventing warping or structural failure. Human spacecraft like the Parker Solar Probe, which makes close passes by the Sun, use carbon composite heat shields and careful orbit design to avoid overheating. An alien probe would need similar or more advanced technology. Another challenge is radiation. The Sun emits not only visible light but also ultraviolet, X-rays, and charged particles in the solar wind. These can degrade materials and interfere with electronics. A functioning solar collector near the Sun would need shielding or self-repair mechanisms to maintain integrity over time. The fact that 3I-ATLAS, if it is indeed artificial, has survived perihelion intact suggests either robust construction or active maintenance systems. Or it suggests that it is not artificial at all, and the entire energy harvesting hypothesis is projection. The community speculates about what the harvested energy might be used for. One possibility is propulsion. If the probe can convert solar energy into thrust, perhaps through ion drives or electromagnetic acceleration, it could make course corrections or accelerate for the next leg of its journey. Another possibility is communication. Beaming a signal back to a home civilization across interstellar distances requires enormous power. A close solar pass might provide the energy budget needed for a high-powered transmission. A third possibility is internal operations, running onboard computers, life support if there are passengers, or scientific instruments collecting data on our solar system. There is also the mothership hypothesis. Tiago and others believe that 3I-ATLAS itself is the main vessel, and that smaller probes like Chris's triangle are deployed for close-range operations. The mothership would remain at a safer distance while the probes venture close to the Sun, collect energy, and return. This is analogous to how human space missions use landers or rovers deployed from an orbiting spacecraft. It is a logical operational architecture if you want to maximize safety and versatility. But it also multiplies the number of objects that need to exist for the hypothesis to be true. You need the comet-sized mothership plus multiple smaller geometric probes, all of which must somehow evade detection by professional observatories. The more components you add, the more fragile the hypothesis becomes. The energy harvesting theory also raises questions about motive. If an alien civilization has the technology for interstellar travel, why do they need to refuel at stars? Presumably they would have advanced energy storage or even onboard fusion reactors. The need to make close solar passes suggests either energy scarcity or mission design choices we do not fully understand. Perhaps interstellar travel is so energy intensive that even advanced civilizations must take advantage of every available resource. Or perhaps the close pass serves multiple purposes: energy collection plus data gathering plus trajectory adjustment, making it an efficient use of time. If you accept the energy harvesting hypothesis, even provisionally, Chris's triangle becomes more than just a weird image. It becomes evidence of an operational mission, a piece of technology performing a specific function. The geometric shape makes sense in that context. A flat, reflective surface optimized for collecting sunlight. But acceptance requires a leap. You have to believe that the triangle is real, that it is not an artifact, and that its proximity to the Sun is not coincidental. That is a lot to accept based on a single unverified photograph. Yet the hypothesis is internally consistent. It fits the facts, even if it does not require them. Part 11. Recent astronomy news, polarimetry and composition surprises. While the fringe community has been focused on triangles and conspiracies, professional astronomers have been conducting their own studies of 3I-ATLAS. One of the most intriguing recent results comes from polarimetric observations, measurements of how light reflected from the object is polarized. Polarization occurs when light waves oscillate in a preferred direction rather than randomly. For comets and asteroids, polarization depends on the size and composition of dust particles in the coma and tail. By measuring polarization at different wavelengths and phase angles, Astronomers can infer properties of the dust that are difficult to determine through photometry alone. A preprint recently appeared on ARXiv, the online repository for scientific papers, reporting polarimetric observations of 3I-ATLAS using the Very Large Telescope in Chile, equipped with the FFORS-2 instrument. The results were surprising. The degree of polarization was higher than expected for a typical comet at similar phase angles. Specifically, the polarization fraction reached values that normally indicate unusually small or unusually reflective dust grains. This could mean that 3I-ATLAS is shedding dust with a different size distribution than most comets, possibly due to unusual surface composition or a different thermal history. For the fringe community, this result is tantalizing. Unusual polarization could, if you squint, be interpreted as evidence of artificial surfaces or coatings. A manufactured object might have reflective properties that differ from natural rock and ice. But professional astronomers interpret the result more conservatively. Polarization anomalies have been observed in other comets and are typically attributed to variations in ice-to-dust ratios, grain-shape distributions, or space weathering effects. The anomaly is interesting, but it is not a smoking gun. The polarization data also allows researchers to estimate the albedo, or reflectivity, of the dust. 3I-ATLAS appears to have a relatively low albedo, meaning the dust is dark, absorbing most of the sunlight rather than reflecting it. This is consistent with carbonaceous material, organic compounds and silicates, all common in comets. But again, the exact values are unusual. They sit at the edge of the expected range, not far enough outside to be definitively anomalous, but close enough to raise eyebrows. In science, these edge cases are where discoveries happen. An anomaly that is just barely significant can either be noise, or it can be the first hint of something genuinely new. One of the challenges with polarimetric data is that it requires careful calibration. The measurements are sensitive to instrument alignment, atmospheric conditions, and the precise geometry of the observation. Small errors can produce large changes in the inferred polarization fraction. Professional groups like the one using the Very Large Telescope have protocols to minimize these errors, but they are not infallible. Independent confirmation from another observatory using different instruments would strengthen the result. As of now, I am not aware of such confirmation. The polarization anomaly remains a single data point curiosity. What would the polarization tell us if 3I-ATLAS were artificial? Manufactured surfaces tend to have uniform reflectance properties, whereas natural surfaces are rough and heterogeneous. If the polarization signature were unusually smooth across different wavelengths, that might suggest an engineered coating. But the opposite could also be true. An advanced civilization might intentionally roughen the surface to mimic natural objects, avoiding detection. Without knowing what an alien probe is supposed to look like, interpreting anomalies becomes a Rorschach test. You see what you expect to see. The professional astronomy community will continue to monitor 3I-ATLAS as it moves away from the Sun. Polarimetric observations at different phase angles and heliocentric distances will provide additional data points. If the polarization anomaly persists and cannot be explained by standard cometry models, it will warrant deeper investigation. New hypotheses will be proposed, tested, and refined. This is how science works. Slowly, methodically, without the drama of live streams and community speculation, but also without the urgency. Professionals have other projects, other priorities. 3I-ATLAS is one object among many. For Tiago and his community, it is everything. Part 12. Recent Astronomy News. Water, Volatiles Detection. Another significant development in the professional study of 3I-ATLAS is the detection of water vapour and other volatile compounds. Observations using ultraviolet and infrared spectroscopy from space-based telescopes like SWIFT and ground-based facilities have identified emission lines characteristic of water, carbon monoxide, and possibly hydroxyl radicals. These detections are strong evidence that 3I-ATLAS is outgassing, losing mass as ices sublimate under solar heating. This is exactly what you expect from a natural comet. The mass loss rate, estimated from the strength of the emission lines, is consistent with a nucleus several kilometers across, composed primarily of water ice mixed with dust and organics. The gas production rate increases as the object approaches perihelion and decreases as it moves away, following the expected pattern for a solar-heated body. There are no obvious anomalies in the timing or magnitude of the outgassing. Everything fits the standard comet model. For mainstream astronomers, this is reassuring. It suggests that 3I-ATLAS, despite its interstellar origin, behaves like comets we have studied for decades. But the detection of volatiles does not automatically rule out the artificial hypothesis. A sufficiently advanced probe might incorporate ice as a thermal management system. Water is an excellent coolant. As it sublimates near the Sun, it carries away heat, preventing the structure from overheating. The observed outgassing could be intentional, a designed feature rather than a natural process. This is, admittedly, a stretch. It requires assuming that aliens would build a probe that mimics natural comet behaviour so convincingly that even detailed spectroscopy cannot distinguish it. Possible, perhaps, likely. That is harder to justify. The composition of the volatiles also provides clues. The ratio of carbon monoxide to water, the presence or absence of certain organic molecules, and the isotopic composition of hydrogen and oxygen can all reveal information about where and how the object formed. If 3I-ATLAS has a composition similar to comets in our solar system, that suggests a common origin, perhaps both formed in protoplanetary disks with similar chemistry. If the composition is unusual, that might indicate the object formed in a very different environment, possibly around a star with different elemental abundances. So far, the available spectroscopic data suggests the composition is broadly similar to solar system comets, but more detailed analysis is needed. One detail that caught the attention of the community is the timing of certain brightness spikes relative to the detection of volatiles. Some observers noted that the brightness increased shortly before or after spectroscopic observations showed a surge in water vapor production. This correlation is expected if brightness is caused by sunlight reflecting off dust released during outgassing. But a few community members speculate that the brightness spike could have been caused by the probe activating systems that require energy, leading to localized heating and additional outgassing. This is reading a lot into coincidental timing, but it illustrates how the same data can support wildly different interpretations depending on your prior assumptions. The presence of organic molecules is also intriguing. Comets are known to contain complex organics, the building blocks of life. Some contain amino acids and other prebiotic compounds. If 3I-ATLAS is carrying similar material, it raises the possibility that interstellar comets could have delivered organic chemistry to early Earth, seeding the planet with the ingredients necessary for life. This is a well-established scientific hypothesis, supported by studies of meteorites and sample return missions. But in the context of the alien probe theory, organics take on a different significance. Could they be remnants of biological processes from the probe's home world? Could they be intentional cargo, samples collected from other systems? These questions cannot be answered with current data, but they fuel speculation. The volatile detection does shift the probability landscape. Natural explanations for 3I-ATLAS are now stronger. The presence of water and carbon monoxide, the typical behaviour of cometary outgassing, and the lack of obvious engineering signatures all support the comet hypothesis. But anomalies remain. The polarization results, the unusual trajectory, the geometric shape in Chris's photograph. These pieces do not fit neatly into the natural framework. The challenge is weighing them appropriately. How much evidence does it take to overturn the default assumption that interstellar objects are natural? The answer depends on who you ask. Part 13. Mission News Intersection. ESA's Hera and 3I-ATLAS. One of the more fascinating possibilities in this unfolding story is that a spacecraft mission, designed for an entirely different purpose, might accidentally provide data relevant to the 3I-ATLAS mystery. The European Space Agency's Hera mission, launched in October 2024, is currently en route to the binary asteroid system Didymos. Its primary goal is to study the aftermath of NASA's DART impact, which deliberately crashed a spacecraft into the smaller asteroid Dimorphos to test planetary defense techniques. Hera carries instruments to measure the crater, the altered orbit, and the internal structure of the asteroid. But Hera's trajectory through the inner solar system means it will be observing a region of space that overlaps, at least partially, with the tail and debris field of 3I-ATLAS. The question is whether Hera's instruments, which include cameras, spectrometers, and dust analyzers, will detect anything unusual. If 3I-ATLAS is shedding dust composed of unusual materials, or if there are small objects like Chris's triangle embedded in the tail, Hera might pick them up. the spacecraft's dust analyzer is designed to measure the composition and velocity of particles, providing data that could distinguish natural cometary dust from engineered fragments. A single anomalous particle detection showing unusual hardness, composition, or reflectance would be enough to trigger further investigation. The challenge is that Hera is not tasked with observing 3I-ATLAS. Its instruments are pointed at Didymos, not the surrounding space. Any detection of 3I-ATLAS-related material would be incidental, a bonus science opportunity rather than a primary objective. Mission planners have limited time and resources. They are focused on the asteroid, not on chasing speculative leads. But space missions have a history of serendipitous discoveries. The Galileo spacecraft, en route to Jupiter, detected an asteroid moon for the first time. The Voyager probes, designed to study the outer planets, provided data on interstellar space. If Hera's path crosses the tail of 3I-ATLAS at the right time, we might learn something unexpected. There is also the possibility of a targeted observation. If enough interest builds within the scientific community, if the polarization anomalies and amateur photographs generate sufficient buzz, mission controllers might authorize a brief deviation to point Hera's cameras toward the coordinates where 3I-ATLAS was last observed. This would require convincing ESA that the opportunity is scientifically valuable, which is a high bar to clear. But it is not impossible. Space agencies have redirected missions before when compelling targets of opportunity arise. The key is demonstrating that the potential payoff justifies the risk and resource expenditure. For the fringe community, the idea that a professional spacecraft might validate their claims is both exciting and nerve-wracking. If Hera detects something anomalous, it would be vindication, proof that the amateurs were onto something. But if Hera finds nothing, if the tail dust is entirely normal and there are no geometric objects, the narrative collapses. The triangle becomes an artifact. The energy harvesting hypothesis is debunked. Everything returns to the standard model of natural comets. The stakes are high, and the community knows it. Another mission worth watching is the Parker Solar Probe, a NASA spacecraft designed to study the Sun's corona by making extremely close passes. Parker's orbit brings it within a few million kilometers of the Sun's surface, closer than any human-made object has ever ventured. Its instruments measure solar wind, magnetic fields, and energetic particles. If 3I-ATLAS or any associated probes pass through regions that Parker has sampled, there might be indirect evidence in the data. A sudden spike in dust concentration, an unusual particle composition, or a localized magnetic disturbance could all be signatures of something anomalous. But again, this would require someone to look for it, to sift through the data with the specific hypothesis in mind. The intersection of professional missions with fringe theories is always fraught. Professionals are trained to be skeptical, to demand extraordinary evidence for extraordinary claims. They are unlikely to take Chris's triangle seriously without rigorous validation. But they are also opportunists. If there is a chance, however small, that 3I-ATLAS is something unprecedented, they will want to be the ones to confirm it. The tension between skepticism and curiosity drives science forward. In this case, it might also determine how the 3I-ATLAS story ends. Part 14. Wider Fringe, AI. Physics theme, AI-generated anomaly. Detection and pattern recognition. Artificial intelligence is changing how we search for anomalies in the cosmos. For centuries, astronomy has been a human endeavour, a person staring through glass, sketching what they saw, trying to capture fleeting patterns of light. But the modern sky is no longer something a single mind can comprehend. Every night, telescopes across the world and in orbit around Earth collect more data than any human could review in a lifetime. Billions of pixels, millions of light curves, endless waves of radio noise. Hidden in all that data could be something extraordinary, a hint of the unknown, a fragment of something artificial, something not from here. Traditionally, the process of discovery depended on patience and intuition. Astronomers manually inspected images, scanned through brightness graphs, and relied on instinct to spot what didn't belong. But the human eye is fallible. It tires, it skips, it interprets what it expects to see. A subtle deviation, a tiny, fast-moving object, or a dim, asymmetric signal could easily go unnoticed. Enter machine learning, a revolution that replaces attention with algorithmic precision. Neural networks, especially convolutional architectures modelled loosely on the human visual cortex, can be trained to identify features across millions of images. They learn to recognise what a normal star, comet or galaxy looks like, and then to notice what doesn't fit. Already, these systems are used to detect exoplanets by analysing dips in starlight, classify galaxies by shape, and flag transient events such as supernovae or gamma-ray bursts. The speed and scale of this technology are unmatched. It can review in seconds what would take human teams years. So here is the provocative question. Could we use that same power to find evidence of artificiality in space? Could AI become our telescope into the unknown, not just finding planets or asteroids, but things that do not behave as nature dictates? Imagine an AI trained on thousands of high-resolution solar images from the Solar Dynamics Observatory and ground-based observatories. It learns every type of solar structure, sunspots, prominences, coronal loops, and flares. It understands the rhythm of the star, the fluid chaos of magnetism and plasma. Then, one day, it is fed a new image and stops. A patch of darkness, a shape that is too sharp, too defined, a triangle, crisp against the roiling surface of the sun. The AI doesn't know what it's looking at. It simply knows, this doesn't fit. That, in essence, is what anomaly detection is. The machine doesn't declare alienprobe. It simply raises its digital hand and says, something here is different. In the context of Tiago's community, the network of amateur astronomers tracking the mysterious interstellar object 3I-ATLAS, this kind of technology could be transformative. Right now, most of the work is manual. Tiago live-streams his telescope feeds, reviews footage frame by frame, and compares results with viewers. When Chris Green, a viewer from Texas, captured that now infamous dark triangle near a sunspot using a Herschel wedge filter, it was a human-driven discovery, a single observer noticing something strange. But what if every observer in that community had an AI co-pilot? Picture this. Tiago's solar telescope feed runs through an AI plugin, perhaps open source, perhaps built by the community itself. The AI continuously compares each frame against a learned model of normal solar behaviour. When something deviates, a flicker, a shadow, an angular pattern, it flags the frame in real time. Tiago doesn't have to sift through endless footage. The system highlights the precise seconds worth his attention. Multiply that across hundreds of observers around the world, each using similar tools, and suddenly you have a distributed AI-assisted network scanning the sun around the clock. This is not science fiction. The infrastructure already exists. Projects like SETI's Breakthrough Listen use AI to comb through radio telescope data, filtering out terrestrial interference and identifying signals with patterns too structured to be random. In 2021, AI systems identified over 1 million candidate signals. Most were mundane, reflections, satellites, background noise, but a few remained unexplained, triggering deeper investigation. The same principle could be applied to optical astronomy. The technical challenge, however, lies in training. Machine learning thrives on examples, labelled data showing what is normal and what is not. For solar imagery, we have immense archives of normalcy, decades of sunspot records, flare catalogues, coronal mass ejection data. But what about the anomalies? How many confirmed images of artificial objects near the sun do we possess? None. Not one. This creates a kind of paradox. How do you train an AI to recognise something that may not exist or has never been confirmed? Without examples, the machine cannot learn the difference between the extraordinary and the erroneous. This is known as the bootstrapping problem. To detect anomalies, you first need anomalies. One solution is unsupervised learning. Instead of telling the AI what to look for, you let it teach itself what normal looks like, and then highlight whatever breaks that pattern. Techniques like autoencoders work by compressing and reconstructing images. If the reconstruction fails, meaning the system can't recreate what it saw, the input is labelled as anomalous. In that framework, Chris's triangle would produce a huge reconstruction error. The AI wouldn't understand it, and that ignorance itself becomes the signal. If implemented correctly, such systems could operate continuously, generating real-time alerts whenever the sun does something uncharacteristic. A global network of amateurs could respond instantly to those alerts, coordinating telescopes to capture additional data. It would be the birth of a crowdsourced AI-powered anomaly detection grid, decentralized, adaptive, and nearly impossible to suppress. That last point matters. One of Tiago's recurring claims is that institutions like NASA and ESA are deliberately hiding information, invoking, controversially, the government shutdown as an excuse for data gaps around 3I-ATLAS. Whether or not one believes that, the democratization of observation changes the balance of power. When discovery is distributed, no single entity can fully control the narrative. AI could thus become not just a scientific tool, but a political one, empowering independent researchers to verify or challenge official claims. Yet as with all technologies, there are philosophical and ethical dimensions. If AI becomes our primary filter for identifying anomalies, we inherit its biases rooted in our own assumptions. Train an algorithm to find geometric shapes, and it will find them everywhere, even where they don't exist. Train it to detect motion consistent with comets, and it might overlook engineered objects mimicking natural trajectories. AI reflects human curiosity, but also human blindness. We risk building systems that reinforce our expectations rather than challenge them. There's a deeper irony here. In trying to automate discovery, we might automate belief. The AI flags an image. We react. We treat its output as a revelation, forgetting that it only mirrors what it was built to see. This raises uncomfortable questions about agency and truth. If the next alien artifact is first identified not by a person but by an algorithm, who gets credit? Who gets to decide if it's real? Consider how this could play out when 3I-ATLAS re-emerges from behind the Sun in early 2026. Tiago's AI-assisted telescope setup pings with alerts. Chris's network in Texas reports similar anomalies. Observers in Spain, South Africa and Japan confirm synchronous detections, all flagged by independent AI systems trained differently. The patterns align: triangular silhouettes, consistent geometry, reproducible data. At that point, the conversation changes. It's no longer a matter of opinion or coincidence. It becomes evidence, distributed, time-stamped, statistically significant. That kind of convergence would force mainstream institutions to respond. The discovery wouldn't belong to a single lab or observatory. It would be decentralized science, open verification in real time. This model is already emerging in astrophysics, where open-source AI tools like AstroML and DeepAstroNet allow amateurs to process data once reserved for professionals. When scaled to solar observation, such systems could reveal patterns no centralized agency could ever suppress or ignore. But there's a shadow side. AI, like any tool, can amplify misinformation just as easily as it amplifies truth. If the algorithms or datasets are manipulated, intentionally or accidentally, false anomalies could proliferate. A miscalibrated system could generate triangles from noise, fueling hysteria and conspiracy. The line between discovery and delusion would blur even further. Tiago's followers already walk that line. For many, the pursuit is not just about astronomy. It's about faith in independent discovery, about reclaiming agency from institutions they no longer trust. AI could either validate that independence or entrench new dependencies, replacing institutional authority with algorithmic authority. In one case, the scientist in the white coat says, "This is natural." In the other, the neural network says, "This is anomalous." Both demand trust. Both can be wrong. And yet, dismissing AI's potential outright would be a mistake. The universe is vast and dynamic. Human attention, finite. Even professional observatories miss things. The first interstellar visitor, Oumuamua, was only detected after it had already passed perihelion and was leaving the solar system. Had an AI anomaly detector been watching, it might have noticed the trajectory sooner. The same could be true for future visitors, or for artificial ones hiding in plain sight. We might even imagine a near-future hybrid system, humans and machines working together. AI handles the data deluge, millions of images, terabytes of light curves, while human observers interpret and contextualize the anomalies it flags. It's not about replacing astronomers, but augmenting them, extending their reach beyond the limits of fatigue and expectation. The precedent exists. In 2023, AI systems used at the Zwicky Transient Facility identified a previously unclassified type of supernova that defied existing models. In 2024, deep learning algorithms help detect gravitational wave events faster than any manual method. Each step brings us closer to a world where machines notice first and humans follow with interpretation. So when 3I-ATLAS emerges again, dimmer, faster, receding into the dark, the question won't just be what it is, but who will see it first. Will it be Tiago staring through his telescope in the early morning hours? Or will it be an algorithm quietly running on a cloud server, silently flagging a pattern before any human eyes even look? There's something haunting in that possibility. Discovery used to be an act of wonder, a moment of human awe. Now it might arrive as a push notification, a message that reads, "Anomaly detected, review recommended," but maybe that's not a loss. Maybe it's evolution. The universe has always been bigger than us. If it takes machines to help us perceive its secrets, then so be it. After all, intelligence, artificial or otherwise, is just another way for the cosmos to look back at itself. When Tiago next points his telescope toward the sun, he will not be alone. His audience will be there, his AI system will be there, and somewhere perhaps, a dark triangular shadow will pass across the star's burning face. Whether it is artifact or illusion, signal or noise, the act of looking, amplified by technology and shared across the planet, will bring us closer to understanding what's real. And that, perhaps, is the true significance of this moment. Artificial intelligence may not find aliens for us, but it is teaching us how to see differently, to look beyond our assumptions, to question our perceptions, and to recognize that discovery itself is evolving. When the next anomaly appears, whether in a telescope feed, a radio signal, or a reconstruction error from a neural network, it will challenge us to decide what we believe. The algorithm will show us a pattern, but meaning will still belong to us. And if that meaning points to something not of this earth, if, hidden in the data, a machine finds evidence that we are not alone, then the first whisper of that revelation may not come from a voice or a transmission. It may come from a single line of text on a computer screen, blinking quietly in the dark. Unclassified object detected. Confidence level, 90%. When that day comes, the line between machine perception and human belief will blur completely. But one truth will remain: we will have taught the universe to help us find itself. Part 15, Wrap and Future Outlook. We are standing at the edge of something. It might be the edge of discovery, the threshold of an epical revelation, the instant when humanity confirms it is not alone in the universe. Or it might be the edge of delusion, a collective mirage born from human longing, a misreading of light and noise shaped by the desire to believe. Right now, as the interstellar visitor known as 3I-ATLAS slips behind the sun's blinding glare, we cannot know which. But one fact is beyond dispute. For the first time in history, ordinary people, amateur astronomers with backyard telescopes and streaming setups, are participating in real time in one of the great cosmic mysteries of our era. The tools of discovery are no longer confined to observatories and billion-dollar missions. The democratization of astronomy, the cheap CCD cameras, open-source orbital data, and online image stacking tools, has given rise to a new kind of explorer. Anyone with patience, curiosity, and an unfiltered sense of wonder can now chase the unknown. And that's exactly what's happening. Here's what's certain. 3I-ATLAS is the third confirmed interstellar object ever detected, following 1I Oumuamua in 2017 and 2I Borisov in 2019. Its trajectory is unmistakably hyperbolic. It came from outside our solar system and will leave it forever. Calculations show that it passed perilously close to the Sun at perihelion, enduring temperatures and radiation that would vaporize most known comets. Yet, unlike typical comets, its behavior doesn't quite fit the models. Polarimetric studies, specifically those using instruments like the VLT's Force 2, have shown unusual dust properties, suggesting an atypical composition or microstructure. Its brightness fluctuates in ways that don't line up perfectly with simple rotation or outgassing cycles. Spectroscopic data does confirm the presence of water and volatile compounds, lending weight to a natural interpretation, a comet from another star. But even these results are ambiguous. The spectrum can also fit scenarios involving highly processed materials, such as silicates baked under intense stellar radiation. In short, the science confirms that something is there, something real, physical and dynamic, but not entirely ordinary. And then there's the human story, the one that transformed an obscure data point in a NASA bulletin into a viral cosmic mystery. Tiago, a soft-spoken amateur astronomer from Brazil with a modest YouTube channel called Dobsonian Power, began live-streaming his observations of 3I-ATLAS. His viewers watched him tinker with his solar prominence telescope, track coordinates from the minor planet center, and talk through the frustration of atmospheric interference and camera noise. What he captured, after weeks of attempts, was ambiguous. A faint blob, a flicker. Something weird but inconclusive. Then came Chris Green, a viewer from Texas, another amateur but with a different approach. Chris wasn't using a prominence scope, he was using a Herschel wedge, a tool that allows safe, high-contrast observation of the sun's photosphere, the layer just above its visible surface. Chris's setup was simple but powerful. A refractor telescope, solar continuum filter, high-speed camera, and patience. What he recorded left even the skeptics blinking. Near a large sunspot cluster, a dark, sharply defined triangle appeared. Not fuzzy, not amorphous, but precise, geometric. A shape that nature rarely produces in that environment. When Tiago received the images, he said only 6 words. "Chris, you won. I'm switching methods." That moment, a small, quiet concession from one hobbyist to another, rippled through online forums, Telegram groups, and Discord servers like a seismic shock. Because if Tiago's blob was the mothership, then Chris's triangle was its probe, one of a possible swarm refueling near the sun. Within hours, the community had constructed a hypothesis both breathtaking and terrifying in its internal logic. The idea went like this. 3I-ATLAS is not a natural object at all, but a vast alien craft, perhaps the size of a city, perhaps hollow, that entered our system deliberately. The smaller, triangular objects seen near the sun are its drones or refueling stations, drawing energy directly from the solar plasma. Supporters pointed out that many human-engineered spacecraft use similar strategies, approaching power sources to recharge or slingshot around massive bodies for momentum. They cited Avi Loeb's controversial 2018 claim that Oumuamua could have been an alien solar sail, and extended it to 3I-ATLAS. Perhaps this was the next one. The evidence was thin, the images ambiguous, but the pattern recognition instinct of the human brain is powerful. Once you see the triangle, you can't unsee it. But the mystery is colliding with an inconvenient astronomical truth. Solar conjunction. That's when an object passes so close to the sun's line of sight that the glare overwhelms any attempt to observe it. For Earth-based observers, it's like trying to spot a firefly against a searchlight. As 3I-ATLAS moves behind the sun, it becomes invisible, not just to backyard astronomers, but to the most advanced instruments in orbit. Even spacecraft like SOHO and Stereo have blind spots near perihelion. For Tiago and Chris, time is running out. Every day the angle narrows, every attempt risks frying a sensor or a retina, and beyond that point, the object will vanish completely for weeks or even months. Professional observatories have more advanced adaptive optics and infrared instruments, but even they will hit the same limit. Once 3I-ATLAS disappears into the solar glare, no one will see it until early 2026, when it re-emerges from behind the sun and begins its long escape from the solar system. By then, it will be fainter, colder, and farther away, a dwindling ember in the dark. If the triangle is real, if the probe theory holds any truth, this may be the last chance to prove it. Miss the window, and the evidence is gone forever. This is the point where science and belief diverge. If Chris's triangle is confirmed, if multiple observers in different locations with different instruments record the same geometry, then the conversation changes overnight. That would mean an object of unknown origin behaving in a non-random, non-natural way near the sun. The implications would be seismic, but if no one replicates it, if Tiago's new setup fails to capture it, the simpler explanations return to the foreground. Optical artifacts caused by reflections in the wedge or filter, sensor interference from solar intensity fluctuations, software processing errors in image stacking, misidentified solar granules or magnetic shadows near sunspots. A triangle can appear out of chaos if you look hard enough. It can also be nothing more than coincidence. This is the crucible of modern discovery, the narrow gap between data and interpretation. Regardless of outcome, The implications of this episode are profound. If 3I-ATLAS turns out to be artificial, we have witnessed the first undeniable evidence of extraterrestrial technology. Not a signal, not a speculation, but physical presence. The first proof that intelligence beyond Earth exists and that it travels. That would change everything. Religion, philosophy, geopolitics, economics and science would all be reshaped in its wake. Nations would scramble to claim proximity to the discovery. Space agencies would pivot overnight. The question of "are we alone?" would finally have an answer, but 1,000 new questions would take its place. Who sent it? Why now? And how many others are there? But if 3I-ATLAS is simply a comet, a natural interstellar wanderer, that too carries weight. It means we are living in an age where cosmic visitors are now detectable, where our instruments and networks are powerful enough to spot the rarest of phenomena. It means that the public, through people like Tiago and Chris, are no longer passive spectators in cosmic discovery. This is the quiet revolution happening beneath the headlines. For most of human history, astronomy was the domain of the privileged few, scholars, priests, or institutions with state funding. But today, the lines are blurred. The boundary between professional and amateur has dissolved. Tiago and Chris are not anomalies. They are prototypes of a new era of participatory science. When their footage goes viral, it is analysed by thousands of independent enthusiasts across continents in real time. Some of them have PhDs, some are teenagers, but all share the same drive, to know what's out there. And in that sense, whether the triangle is real or not, something extraordinary is already happening. The collective awakening of distributed curiosity. Now comes the hardest part, waiting. Solar conjunction forces a pause on all observation. For weeks or months, 3I-ATLAS is hidden behind the sun, untouchable, unseen. Tiago will continue streaming, dissecting old footage frame by frame. Chris will refine his calibration techniques. Online forums will build models of orbital motion, trying to predict where the object will emerge. Meanwhile, professional astronomers will publish new papers on polarimetric data, on dust grain scattering, on volatile ratios. The ESA Hera mission will quietly continue its trajectory, potentially crossing a fragment trail left behind by the object. And somewhere beyond the reach of human eyes, an interstellar traveller is passing closest to our star, tracing an arc through space-time that began light years away. The entire human conversation, all the speculation, all the disbelief, all the wonder, depends on what happens next. And that leads us to the most uncomfortable question of all. If you saw a perfect geometric triangle hovering near the solar surface, during the exact window when an interstellar object was visible, what would you believe? Would you accept NASA's position that it's an optical illusion, a trick of light and heat? Or would you trust the independent observer who captured it, believing that truth can sometimes come from outside institutions? There's no easy answer. Belief in science requires skepticism, but belief in progress requires imagination. The line between them is razor thin. Our faith in consensus, in peer review, in controlled experiments, is what keeps us anchored to reality. But every major discovery in history began with someone refusing to accept consensus. The courage to look again, to question, to risk ridicule, that is how knowledge advances. 3I-ATLAS will reappear in the sky sometime in early 2026. By then, it will be fainter, smaller, harder to track, but not gone. Tiago plans to be ready, with upgraded optics, a Herschel wedge of his own, and a new team of collaborators spread across time zones to capture simultaneous data. If the triangle appears again, if two independent observers in different hemispheres record the same shape, at the same coordinates, it would be one of the most important amateur discoveries in modern astronomy. If it does not, then the mystery fades back into the domain of imagination, joining the long history of cosmic anomalies that never quite proved what we hoped. Either way, the story doesn't end. Because the real phenomenon here isn't just a triangle near the sun, it's the conversation around it. It's the way thousands of people from around the world looked up, questioned authority, and tried to see for themselves. In that sense, 3I-ATLAS has already changed us. It has reminded us that curiosity is not a privilege, it's a birthright. Somewhere behind the sun, a fragment of another star system is carving a luminous path through the void. Whether it is rock, ice, or something built, it carries with it the reminder that the universe still holds secrets, and that we are, all of us, still learning how to see. So when 3I-ATLAS emerges again, the world will watch. Tiago will have his telescope ready, Chris will have his filters cleaned, and millions of us will be there too, not scientists, not skeptics, not believers, but witnesses. Because when the light fades and the triangle returns, the question won't just be about aliens or comets, it will be about us, about how we choose to interpret the unknown, about whether we reach for the extraordinary or retreat to the safe and familiar. The sun hides more than it reveals. And somewhere in that blinding light, truth waits, patient, indifferent, eternal. We are standing at the edge of something, and whatever it is, discovery or delusion, it's already begun.